All right, welcome everybody. We're going to talk about the Linux user kernel ABI. So we're going to cover a bunch of stuff. Please, I'd much prefer just jump in at any point if anything's not clear or wrong. All right, I usually learn at least one thing every time I give a talk. So if anything's wrong or there's an addition or a question, just shout, and the more interactive and flowing we can be, and I'm happiest if I get no more than halfway through my slides. So this is, in theory, some of the stuff that we'll cover. We'll see how we go. Just kind of background to this. So I've spent the last, well, depending on how you count, 1 or 2 decades building this time-traveling debugger, which works by replaying from a snapshot and make sure that you replay exactly everything that the system did. So we have to capture at the record time everything. So the most trivial thing is like, a read system call. Well, if I read 12 bytes off file descriptor 4, that's really simple, right? I can just cache that away, and then when I'm replaying, I can just reconstruct that super easily, plus the return code, of course. We'll talk about that in a moment. But there's way more to it than that, right? And it gets really interesting, I think, with how signals work and system calls get restarted and how this stuff all actually works. I think this is useful. Obviously, it's useful if, well, let's get to this. So most of the time when you're writing a program, you are not talking to the kernel directly. You're talking to maybe STL or some other libraries, and then underneath that, libc. And libc kind of gives you a model of the kernel-like interface. It's not quite what the kernel is doing. And most of the time we don't care, but there's at least a couple of times when we would care. One is if we're writing the library, if we're writing libc or some equivalent, we're writing right down to the kernel ABI, which can happen. Happens to me, probably could happen to you at some point. The other time is when you're trying to debug something that's super weird and messed up, right? And your only kind of recourse is to attach the debugger to the running process or run with strace or something, and you're trying to work out what's going on. And if you don't really understand what's happening, then you can really get led astray by some of the results that you're seeing or you think you're seeing. Plus, reason number 3, I think, it's just kind of interesting, right? It's kind of cool. So, yeah. So just a note then that the Linux kernel does not present the POSIX API. So when I started on this journey with Undo, I thought I knew POSIX pretty well. I'd even read the book, maybe kind of cover to cover. And that was kind of the model that libc presents is like good enough that it can fool you for a long time. And that's what the kernel is actually doing. But yeah, it turns out not quite. And like always, when the models are almost right, that's when you can get most confused in the kind of uncanny valley. So yes.
And stupid question. glibc is distinct from libc in which way? You say GC.
Oh, sorry. Yeah, that's just because I'm lazy with my slides and inconsistent and just generally a bit sloppy.
Okay.
It's the same thing. Sorry.
Okay,
Yeah. glibc. I think there are other libc implementations, of course. So yeah, there's different kind of versions of this. So maybe libc is the generic one and glibc is an example. I don't know whether the other libcs present POSIX. Did I get away with that? I think that's kind of
they're supposed to get the official API, so they're pretty much bound to do the same.
You're right. They probably do. Okay. Cool. So what even is an operating system? So I think of it like this: that any operating system provides one or more of the following things, right? Protection, security, and services. So by protection, I mean the program A cannot interfere with program B, cannot access its memory, cannot stop it running, cannot do a denial of service attack or anything like that. Even in the case that program A and program B are not trusted and are being run by not trusted people. Security, I think of as like just the policy of defining who does what, and then services, network, file system, etc. So I think things like, say, DOS back in the day or a really small RTOS might provide just services, might not provide any security or protection. I think it's technically possible, although I've not seen it, to provide security without protection if you do not allow, in fact, you do see this on loads of kind of devices and things, if you do not allow untrusted users to run untrusted programs, then you can provide security without providing protection. The Linux kernel, and a microkernel would do protection without doing any security or services. It would leave that all to user space. Linux kernel does all of the above. It's a monolithic kernel. It does a bunch of stuff in user space as well, of course, but it kind of does everything. So it's There's pros and cons. I'm not going to get into that debate here. And what we're interested in, as I say, is this layer between user space and the kernel. So, in a protected operating system, we have to be careful about the way that user mode, untrusted code, can invoke the kernel, right? Because if you just allowed user mode to call like any kernel function or just jump into any point of the kernel, then it'd be impossible to guarantee anything. All kind of security vulnerabilities would be empty. So we need a way that user mode can call into the kernel in a specific way. Really, the only difference between kernel mode, some systems call it supervisor mode, some people call it ring 0, it's all the same. The only thing really that's special is that there are some instructions that are not available in user mode that are available in kernel mode. That's really the only difference. Sometimes some of the virtual address space is not present, is not accessible from user mode, but this has changed in the last couple of years. So it used to be when a user mode application called into the kernel, it would run in the kernel in the same address space as the user mode application. But now the kernel could access a bunch of extra pages because they were marked with the ring 0 accessible bit. That changed a few years ago with the workarounds for Spectre and Meltdown. So now when you call into the kernel, it will put in place a whole new address space. So it really is the only difference now is that there are just some instructions that are not available in user mode. And it's a little bit slower, but they had to do it for security reasons. So the way that we do this, protected, question at the back there.
So, sorry, just to double check, the kernel, when it runs, when I call some kernel, it has a different address space from...
Well, like the first thing it does is to install a new address space. And the instruction required to install a new address space, which on x86 is to move a pointer into CR3, I think, is a privileged instruction that only the kernel is allowed to do.
So if I give it a pointer, it cannot read data from the...
Oh yeah, well it can, but it has to know to direct via the... there's some overlap, the address spaces that overlap, so that it can see the user space. But the point is the kernel pages, in the old days, the kernel pages were like mapped into the user space. It just couldn't access them. It would get a fault if ever it touched them, but the translations were all there. And that was what led to the Spectre and Meltdown bugs. So now that's not the case. So yeah, address spaces can be overlapping.
Does that mean user space now have more? So 32-bit user space now has 4 gigabytes?
I think that's right. Yeah.
Ooh.
I believe so. Yeah.
So there's upside to that.
Yeah. I believe that's the case. Yeah. So there used to be the limit. Used to be that on 32-bit, everything from Auxv up was kernel only. Now I think that restriction. You could already optionally have done that in the old days, but now that's like by default the case. As with all this stuff, you can configure it on or off, but I think pretty much everyone configures it this different address space on now because of those security issues. Cool. So the way that we need a safe way for user mode to invoke a kernel mode function is architecture specific. Here are just some. So on old school Intel or x86 architectures, you do an int soft interrupt OX80. Nothing special in the architecture about that number. That's just what Linus chose in 1990 something, and it's still the one that is used. Different architectures, different ways, and we pass arguments to syscall via registers. And I don't know why, but for some reason the x86-64, which is probably the most common, maybe ARM64 is becoming more common now, but it passes the arguments to syscall in almost exactly the same order that you pass arguments to functions in the C ABI, except arguments 3 and 4 are inversed. So argument 4 goes via RDX.
I opened a Stack Overflow question about that and got an answer, and I don't remember it. Something about syscall. They don't swap. There's one argument that is in a different register.
Yeah.
So if you look, for example, at the glibc implementation of mmap, which needs 6 registers, it does one move and then does syscall.
The other, okay. Maybe I never looked past 3. Yeah. So argument 3 on the C ABI is in RCX.
And they said something about syscall needing that other argument, but like I said, I don't remember the answer.
Okay. That's interesting.
So I asked the question.
Yeah. Anyone else know the answer? Anyone know the answer to that?
I can find you.
I've been sufficiently incurious that I haven't actually looked into why. I just know that's how it is. Cool. All right. So hopefully nice and simple. Let's just see that in action. So here I have, so let's do this one. So here I have like super simple program. It's going to read 1 byte from standard in and do some excellent error checking here, but that will do for our purposes. And let's, I'm going to compile it static because I don't want to get confused with all the system calls going on from the dynamic loader and everything. So we're just going to make that static. I'm going to run that now inside, inside UDB, which is our kind of equivalent to GDB, but it has some extra stuff that I'll show you why in a minute. So if I start the program, go catch syscall. This is a bit like a breakpoint, but it's going to stop at the moment we actually hit a syscall. And now I continue. OK, so now I've hit the syscall inside read. So let me just get the right view here. OK, so I don't know why it does that. But anyway, so let's go. In fact, I'm going to go reverse step I, so I'm just before. So now I'm right before the system call. This is the system. This is the syscall instructions just running on my laptop. And we can see everything I spoke about here, right? So we've got RX is the syscall number, which, yeah, confusingly for read, the syscall number is 0. So you'll think 0 is like some special, doesn't mean anything. It just happens by coincidence on x86, 64. Read is 0, write is 1, etc. And then we've got the arguments. So our DI, where have you gone? This is also 0, which is file descriptor 0, because that's what we're reading from standard in. And then our DX, which is the, RDX is the length, and RSI is the second argument, which is this buffer. So if I just step I that now, we can watch how this goes. So, oh, sorry, let me go back. I forgot to, let me remove the, remove the catch points, otherwise it gets confusing. So let's step I this now. And we're inside the read system call. Okay, so now it's stopped in kind of inside that system call. So if I hit enter, okay, let's refresh the screen. So now that read has returned. It's returned 1 byte in RAX. Also, just note, if I go back one instruction, note that R11 changes as well. So R11 changes from 0 to 246, which is the flags. That's not guaranteed, right? It's just, and I've only ever seen R11 change, but in theory, any of the registers can be changed by this system call. It just mostly puts them back. So it's just something to be aware of if you find yourself writing to syscalls directly.
No, I think there's an ABI about what can and cannot change.
Is that right?
I think there are some volatile registers.
I think, but I've only ever seen R11 changed. I think what you think you'll...
It's RAX, RCX, and R11 are the 3 that it's allowed to change. So it uses RAX for returns, RCX and R11 are allowed to be clobbered.
Oh, they are? Okay, all right, interesting. I've never seen it clobber RCX, but yeah.
So it's not the same as just function call conventions, there's different call
Correct. It's one of those things that's like confusingly similar, but not quite the same. Yeah. So there you go. I learned something already. So RCX and R11 are allowed to be clobbered. Good. All right. Well, that's kind of in a really simple version of how it works. See what it's doing there. So there's different ways of doing these syscalls, and it can get a little bit confusing. So the old school way is this int 80, which is just on x86 is available everywhere, but it's kind of slow, but works. Newer, as in anything from, like, say, 686, that's like 20 plus years ago now, has this sysenter instruction, which is kind of weird in that it's faster than int 80, but it doesn't return back to immediately afterwards. It returns to a pre-programmed return point. So Linux pre-programs the return address of the sysenter to always be the same place. And you also have to have a mostly flat address space. You can't start messing about with segments too much, which I guess no one does anymore, which is a whole other thing I think is really sad. I think there's loads you can do with segments and they're awesome, but that's probably even more niche talk than this. On x86 64, nice and simple, we've got the syscall instruction. So we just issue syscall, and that kind of does what you want. It returns back to where you were, and it's nice and fast and everything. Yes?
If this is too much of a rabbit hole, you don't have to go into it, but what was the debugger doing there with the step instruction? Like, how, when you were stepping, it wasn't just a single instruction. Like,
yeah.
How does it know? I guess, like, my thinking of a debugger is usually like it knows to set a breakpoint and substitute in the structure, do
Yeah.
something to say, hey, I want to stop when it gets here. What's it doing on that syscall instruction?
Right.
You sort of step through it twice.
Yeah, so I'm going to go right into that rat hole in just a minute, actually. But an adjacent rat hole. So let's go down this one, and then we'll go down the adjacent one after that. So what that's doing, there's another rat hole, which we may get time to get to, which is ptrace. So GDB and most debuggers are running things under ptrace. There is strace and everything. And there's a ptrace operation called pthreads, which will run you forward until the next time a syscall is entered or exited. This is what strace uses all the time, right? And then it just returns with a special kind of sig trap at the point the syscall happens. And that's what we were doing inside. I was running with a catch syscall to run up and catch the time when a syscall actually happens. And I just was reversing back because I can do that in UDB one instruction.
The other thing he asked about, Ptrace syscall gives you stops twice for every system call. Once before entering and once after returning, before returning control.
And I think it was waiting for your input.
And then it was waiting for my input, correct?
Yeah.
Yeah. So when I did a second step, that was into the system call. Then I disabled the catch point by that point, but then there would be another catch. So you'd go catch point, enter the syscall, then I type enter to complete the syscall, then there would be another catch point to say syscall is returned.
By the way, I found the answer. I posted it on the Discord channel.
And?
Do you want me to read it out?
Is it quite long? All right. If it's not long, we'll
Let's
devour
not hijack
Discord.
this.
Yeah. All right. No, this is good. I like this. There's lots of interaction and I'm learning stuff. So that's nice and simple, except it's never simple. So if you're running 32-bit user space on an x86-64 and you are on AMD, you have to use Syscall, and if you're on Intel, you have to use sysenter on 32-bit. Or you can use int80, but that's a bit slow. So that's a pain. We generally don't like to compile programs having to know which CPU vendor they're running on. So that actually led to that. This was, I think, the beginnings of what led to something that's quite cool, which is the VDSO, the Virtual Dynamic Shared Object. So what they decided to do, we don't want the application to have to be compiled with this instruction or that instruction, depending on what architecture I'm running on. So why don't we just map a page from the kernel into user space, and we'll put whatever instructions are appropriate in that page, and then user space can just call that. That was actually, this predates the VDSO. That was not the VDSO, that was the vsyscall page. So if we, let's come out of that. So can you all read that down at the bottom? I can, can you read
a bunch of enters.
Can you read the, well, yeah, if I do a bunch of enters, it will just repeat, well, I'll do enter, it will repeat the command, that'll do. Fine. So what have we got here? So that down at the bottom, right at the very top, this is a fixed address. This OXFFFFF60000 is the vsyscall page. That, by the way, is where the sysenter thing will be programmed to return back to on 32-bit. And it just contains a bunch of instructions. Notice it's execute only. You can't even read it. But it contains some things that you can call. It used to be readable in the old days, but I don't know why it's not anymore. Security, I guess. So you can call certain well-known offsets in that to do what you want, but it's kind of limited. So then they kind of improved it and came along with the VDSO, which you can see 2 maps higher, which is like a legit shared object, but it doesn't exist on the file system anywhere, at least not unless you're doing a kernel build. It's just plopped into your address space by the kernel.
And so like any sort of fix-ups, security things ever need to get done can be done there?
Although the security things could be anywhere, but you can do security things there. More likely it's just new versions of the kernel work in a slightly different, better way, and now you can do things. So this is what things normally look like. I've got my libc or whatever libraries, they're just mapped. They're just basically M-maps onto the file system. VDSO is this magic thing that's M-mapped up from the kernel. Yes, question?
Are you allowed to jump to any address in the VDSO, or does it enforce that you can only jump to certain points?
Good question. So there are probably these days, there'll almost certainly be the x86 endbra instructions that do some sort of enforcement to make sure that you're only indirect jumping to those, but you could compose a direct branch anywhere into the VDSO because it's just a bunch of instructions, right? So there's no reason you couldn't. So the code in the VDSO runs in user mode. Okay.
Oh, okay.
Right, but it's just provided by the kernel.
It also has some data, right?
Yes, I'll come to that in just a minute.
How do you continue after the sysenter returns to this single address?
Yeah.
Do you have to put your continue address into
No,
the
because you've done a normal call, so your return address is on the stack, and then the syscall return kind of goes via this trampoline thing that just fetches up the stack and then returns to where you are. Yeah. Question.
So there's an overhead, right? You do a call and then a syscall instead of just syscall.
Yeah, although that overhead will be tiny compared to the overhead of doing an OX80 versus just entering and exiting the kernel these days, especially with the address space swapping, is kind of on the order of many thousands of cycles. So yes, but the extra overhead of that indirection is negligible. It might even be zero on modern CPUs. But the cool thing about calling into originally the vsyscall page and more recently VDSO is it usually doesn't actually call into the kernel at all. So if we go so you can see get time of day there's a few functions that are inside, just a few functions that are supplied by the DSO. Note that I'm going to pull this thing up a bit because it's going to be more readable for everyone. So note that, like the debugger just knows about this, right? Because it's just a normal DSO debugger. Well, it knows that it's special, but it doesn't need to know much about it. And we can look at that. So this is provided by the kernel to get the current CPU that you're running on, and there's no syscalls. Same for get time of day. It won't do a syscall. Maybe it does occasionally, but usually it doesn't. So it's way faster. It's really mostly a performance thing, but it also gives it this flexibility. There is also some data, which these days, this is the newest one, is vvar up here just below heap. And that can export various bits of data that are not in any way security sensitive to the process. I don't know actually what's in there. I think some stuff for calculating time of day these days is in there. But the point is different kernels will put whatever they want in there, and it's all kind of invisible. You shouldn't access it directly. Nothing stops you doing so, but probably not wise. You probably just should call the VDSO functions, and they'll access it if they need to. While we're here, I'm going slightly out of order, but while we're here, so there's two other special maps here you can see in square brackets. One is heap, special because that's the map. If you call proc, which is the syscall underlying thing of sproc, then that's the map that will grow. So that's the map where your heap goes by default. There's not really anything special about it. I think these days it's really a legacy thing. Like you could just make a map, and it could just extend the map with there's a syscall, new but newish, newer than proc, I think, emry map. So I'm guessing that proc existed when emry map did not exist. These days you could just do emry map and make your map bigger.
No, it was meant for reserving virtual addresses, so that you wouldn't have allocations that would prevent your heap from expanding. So mmap would only return in 32 days.
Yeah, okay, so that brings us into the stack one, which is has a similar but different. So stack is special because it has the maps grow down. I think anything that has a VM maps grow down attribute will appear as a stack. And it's kind of weird because it will, if the program touches a byte just before the start of that stack map, the kernel will automatically expand the the stack down. But only does that for the main thread. If you're using pthreads and you allocate a bunch of threads, create a bunch of threads, all of which have a stack, they just have regular maps with large virtual address space, and you just rely on the regular kernel demand paging thing to back those with physical memory when they need it. Personally, I don't know why you don't just do that, particularly, on 64-bit address spaces anyway, you just do that, just allocate a large virtual address space. I don't see the advantage in the magic of the automatic grows down. It's just confusing as hell. But that's what it does, and I think that's what it's always done, and it kind of just keeps that compatibility for the main thread of the program. Yeah, there's a question back.
Sorry, I just don't know. sbreak is a call that underlies malloc?
Yeah, so malloc normally just sits in user mode. It's got its chunk of memory, and it just hands you out however many bytes you want from. But then eventually, if you've used that up, it'll then ask for more memory from the operating system, which it'll do by calling the, well, sbreak is the libc call, which it maps onto break, which is the kernel call, the system call, which will then grow that map. So then malloc can continue allocating out of there. As I say, I think maybe there's good reasons on smaller, like 32-bit address spaces to kind of reserve. But then again, I don't see why malloc can't have discontiguous maps.
Because then the heap itself is fragmented.
Right, yeah. So I guess it can be a little bit more efficient to do it that way. Yeah, that makes some sense. Yeah. Does that make sense?
But then in 32-bit, the first gigabyte was off limit because it was the heap, and the last gigabyte was off limit because it was the kernel spaces. Yeah. And you had 4 gigabyte or only 2 gigabyte.
Yeah. So now you've got a bit more available, but then things are getting bigger all the time. So, although then again, these days, if you need the space, just run a 64-bit process, right? So that's heap and stack. So these are sort of these maps that are kind of designed to just grow. Like I say, you can grow any map with emery maps these days.
I'm pretty sure emery map is not, but never mind.
So pretty sure it's what?
I'm pretty sure the emery map is just for changing attributes. You can just mmap to the address you want if you want to grow. But never mind.
You can emery map to grow the map, right?
No, emery map is for taking an existing map and changing its attributes.
Or including attributes, including size. You can even give it a different address. You can move it to a different virtual address.
Okay, but you could always mmap and ask for, since those are addresses that are not backed by any particular. Never mind.
You can continue. Later. Yeah. Anyone else? No. All right. Yes. Oh, yeah. So beware strace. So I'm going to show you. So some of the things you think might be a system call, like get time of day, not. So if I run, so here's function that's going to call get thing that's going to call get time of day. Let's compile that. Again, static, and run that under strace. Yeah, not many system call. I mean, it's static, so we don't expect loads, but there is no get time of day system call there, right? Because it went via the VDSO. Strace doesn't see it. Yeah, talked about all that. Yeah, okay, so Errno, let's talk about Errno very briefly. So yeah, Errno is so if you want to be pedantic, and let's face it, who doesn't like being pedantic? I think the man pages kind of lie. So the manual chapter 2 is for system calls, syscall manual. Manual 3 is for libc. What's
fopen?
Yeah, right. Library functions, right? But if I go to, it says this. It's saying this is a system call, and then it says it returns Errno, and the system call does not return Errno. The system call will return a negative error code between -1 and -4095, No system call is allowed to return that as a legit return address, because even something like mmap that's going to return a pointer can't return a pointer in that very top page, because it's got to be a page-aligned pointer. I don't know what happens if you have a page size smaller than 4K. I don't know if that's allowed or not. Probably, I'm guessing not. I'm guessing 4K is minimum page size. Yeah, so we can. No, let's do my read. My read, and I'm going to run this in GDB this time because I'm going to show you some other stuff as well. That well, let's do it now. So yeah, so UDB that I showed before actually hides you from a couple of the kernel details, which I think is usually what you want. But for this talk, we can trick GDB into exposing some stuff that it's not supposed to. So this is my read program. So I'm going to just run it. And now when I control C, okay, let's get that view source and assembly registers. And so, by the way, oh no, because it's got no source, so right. Control X to, yeah, when it says no assembly available, I don't know why GDB sometimes does that, but you can remind it. Yes, right. So we were inside the syscall here, right? I did Control C to interrupt the read system call, and the return result is -512. Maybe we'll do a little competition for who knows all the Errno and Syscall numbers. There'll be a quiz at the end. -512 is, be forgiven for seeing this because this is the kernel source, and it says these should never be seen by user programs. Although it does say that Ptrace can observe it. So yeah, so minus is minus e restart sys, -512. That's a magic return code, as are these other 513, 14, 515 is different, and 516. These are all magic syscall restart codes that do slightly different things. So when I Control C interrupted that read, now when I continue, what it's going to do, it's actually, I spent an embarrassingly long time writing a debugger before I realized this is what was going on. So I always thought when you Control C interrupted a syscall in Ptrace, it was like in the syscall. It's like the program, the trace process is deep inside the system. That's not what happens. When you interrupt it, it kind of percolates all the way back up to user space, unwinds all the kernel, which I guess it kind of had to do back in the days of the big kernel lock, and sets things up.
It doesn't have anything to do with the kernel. It has to do with the fact that you can't preempt the code in the kernel inside the same thread.
Yeah.
So you have to let the code know that you're exiting so that it can put itself in a state.
Get to a sane state, yeah, but I don't think it would have to necessarily go all the way back to users. But anyway, maybe it does. Anyway, it does, whether it,
we get back to user space one way or another.
It goes all the way back to user space in a special kind of magic way, so that when you do this ptrace continue, it's just going to restart that syscall without you having to do anything. So the debugger or anything doesn't have to like mess about and work out where to put the program counter back to. Even though this looks like when I continue, it's about to resume from here, because it's got that -512, it's actually going to resume from the system call. Okay, so now it's inside the read. I can do enter, and it will then complete because the system call returns, and I was just running that. However,
so can I
yeah.
So I didn't understand. So it will restart the system call from the beginning from any instruction inside the system call?
It will just run the whole. In the case of, so I'm going to get into the case where it's not the case in a minute. But yeah, in the case where it's -512, which is the most common one, it's just going to rerun that system call. Like,
because once the debugger stopped the system call, you said that it's going to restart the system call on continue from the beginning. No?
Yeah. Yeah.
So it doesn't mean, like, how does it can write any state anywhere if I cannot be interrupted on any instruction?
So you interrupted. You mean when you interrupt in an instruction down in the kernel?
Yeah.
That's going to all complete. It's all going to unwind and return. It just returns with this magic error code.
The kernel doesn't get interrupted. The kernel has code that says, I'm now waiting on a mutex or some synchronization context, and it's a interruptible wait. So when you did Control C, that wait returned with a code, error code, standard error code that said, I got a signal. Now the system call said, okay, if you get a system call, I'm going to go out of the system call, and I'm going to return restart system. And then that gets propagated out, and on the code that goes out to user space, the ptrace hook gets called. And so the debugger gets notified. If there's a signal handler, it gets called. And then the system call goes right back.
I had the read. When I read, I moved some number somewhere.
When you move some numbers, you mean read some data?
Yeah, but there's a state that indicates where I read from. I don't know.
Right. So that I see the thing. So the thing is, in the example I did there, I did Control C before any data had been read.
There was no data to read.
There was no data, but no data to read. If I'd read maybe I'd done a read of 1,000 bytes, and I'd so far read 200, and a signal comes in, then the read could return short, or it would return if it depends on what it's reading from.
If it has data, it won't handle.
If it's reading from a file system, it's not going to read short. But if it's reading from, say, the network, and you say read 1,000 bytes off the socket, and it's read 200 bytes, and you control, and it gets a signal, maybe even without the debugger, maybe you just got a signal handler, right? It gets like sigalarm, and your sigalarm handler runs.
I'm sorry, that's not correct.
It can run.
If it has any data to return,
Yeah.
it will not handle the signal. It will return that data, even if it's a short read.
No, it will return. What I'm saying is, it will return the 200 bytes read. Then it will call your sigalarm.
It will not return with the restart sys.
No.
With the amount of data it already.
Yeah, that's what I'm saying. So it will return the 200 bytes read. So you've read 200 of the 1,000 that you asked for. Then it will call your sigalarm handler, and then it will just continue, right? If it hasn't read any bytes yet, that's when, say, maybe to, I don't know if this makes things easier or more complicated, but just to get debuggers out of the way for a moment, because that can kind of cloud things. So I've got no debugger, I'm just running, and I've got a signal handler. And so if I haven't read any bytes, and my sigalarm handler runs, then when it returns, then it's going to return eintra, which is -4, which is -4, and then interrupted, and then your program has to just deal with that. If it's read 200 of the 1,000 bytes, it will just return. So I've read 200 and carry on, and your program has to deal with the fact that it returned short.
So the system call has a behavior for any interrupted any instruction.
It's documented in the
yeah. So most system calls behave like I've just described. Some system calls behave differently. There's also the catch that when your signal handler, you can specify SA restart as a flag, and then that will just cause your system call to restart rather than return eintra. And then it will restart just from where it was. So it's read the 200 bytes, and it will know to restart, just resuming the read from where it was in that case. Chris?
I was going to say, this is fascinating. I've never really thought very much about how automatic resumption for system calls work. Like when GDB was showing we were sitting on a CMP instruction,
yeah.
Was it just mistaken in that case? Like the only thing I don't really understand is how exactly does the system call actually get resumed?
Right.
Is it magic between the OS and the CPU, or was GDB just mistaken about what the instruction was sitting on?
All of the above. So,
okay.
So go back into, actually I meant to show you this, sorry, apologies. Right, so let's run that. So it's in the read, Control C. If I look at my registers, yeah, RAX contains -512, I've got all these general purpose registers, but there's a magic register. Info registers, orig RAX. If that is not -1, it's a system call number, which in this case is 0 because that's read. So there's a little bit of magic between the kernel and user space. And when you do a ptrace continue to resume, it will go, oh, actually, system call. Then it will look at the return code, what's actually in our RAX, minus 512 in this case, to know which kind of restart to do. Because there are different kinds of restart. So there's restart, just run the whole thing again. And if I'm in a read and I've read no bytes from it because there wasn't anything to read, I could just restart it, right? I have that. So far, that system call has had no side effects. It doesn't rely on anything. If I've got no, this one. Okay, so let's compile that. So it's going to sleep for 5 seconds, right? Continue, wait a couple of seconds, interrupt it. So info reg orig RAX is going to be, okay, 230, which is the system call for clock nanosleep. Well done, prize. Yeah, but info registers RAX minus 516, which you will all remember is restart block, which means the kernel has remembered a little bit of information about that syscall, like how far through that syscall has got. So now it's going to restart using a magic syscall, which is the restart syscall. So what will happen? So remember, I interrupted that. That was a 5-second sleep that I interrupted after about 2 seconds. So when I continue, if it didn't do that, if it had minus 512, it's now going to wait for another 5 seconds. But we don't want that. It actually is going to just continue completely. So it's looked at it worked out where the end time was from that 5 seconds and just says, oh, that's elapsed now, so it returns. Yeah.
I believe I heard that in the kernel, you are cooperatively interrupting, that you cannot be interrupted unless you said, hey, this is my point where I can be interrupted. I'm not sure is that true. So is there a fixed number of places where the syscall has to handle interrupt, or it can be interrupted in every instruction?
So you can get interrupted unless the kernel has disabled interrupts, it can get interrupted at any point. Okay, which only disables interrupts for very short periods. But then it's got a choice about whether to like preempt that kernel thread at that point and go and do something else, or get it to a safe place, kind of safe. So it's like it's semi-cooperative, semi-preemptive. Like, because if cooperative multi-threading means you can just go while one and lock the system up, right? And that's like, it will get interrupts and things, but it needs to get to a point where it's a safe place for it to stop. So it gets this into what we were talking about, the interruptible sleep state is a particular state. Might get to some of that stuff. So you can, by the way, sometimes you can see this when things go wrong. You see a process completely stuck and you can't kill it. Even with kill minus 9, you can't kill it.
You're conflating two things, and I think so do you. There's interrupts and there's signals.
Okay.
Interrupts are a hardware thing. They're from an external source, and they can preempt your code anywhere, unless you disable them. Then there's signals. Signals are an operating system construct. And if you're in the kernel, you can only receive them when you do an interruptible wait. And if you do, as long as you're in the kernel and you're not in an interruptible wait, then the state of your process is uninterruptible sleep, the dreaded capital D, and then no signal will arrive, because the kernel does not know how to preempt a user space task in the kernel. The task has to be ready to be interrupted.
But so yes, but so I was maybe asking a slightly different question. But so that is complete yes, and not yes, but yes, and other kernel threads can still run. Okay, so like your system's still fully alive. You can type top. You can see the thing there stuck in the capital D state, uninterruptible sleep. You just can't kill it. Now that is a kernel bug or driver bug, which is part of the kernel. It should never be. The kernel is supposed never to spend extended periods in uninterruptible sleep. But sometimes shit goes wrong, and you can see that. And then the only way to get rid of that process is, I think, to reboot the system.
Sometimes you're lucky.
Sorry?
Sometimes you're lucky.
Or maybe it just comes out of the uninterruptible. You can knock it out in some way, yeah.
So is the restartable, I can use word concept, but like the idea here, is this for debuggers really exclusively like a sort of ability for you to create, or are there other?
Yeah, no, other, because you also got this case we were talking about before, is when you install a signal handler, you can install that with SA restart.
Right.
Uses the same mechanism. And you can also, there are some system calls, like e.g. Futex, which will not return the intra. Will just magically restart. And all this restart kind of mechanism happens. And what happens is when the kernel is resuming, going back from kernel mode, resuming that user mode thread, it knows if it's in this magic restart state. That's the same thing as the REX. And it just magically subtracts 2 on x86 from the program counter before starting, which will go back into the syscall. Unless you're on the mad sysenter thing, which always returns to the same place, which has a hack in the sysenter step. So there's a jump right after the syscall instruction. I can't remember how it works. I just remember the kernel comment from Linus that says something like, I'm a disgusting pig and proud of it. I can't remember the details now. But that's really going into the weeds. But the point is, yeah, all this restart, this magic subtract 2 or 4, depending on what architecture you're on, from the resume address to go back into the syscall. Yeah.
Right. So it's put it another way, like it's a complicated song and dance between kernel and user space that allows me as a user to get the behavior I want.
Yeah.
Sometimes I might want to restart, sometimes I wouldn't. I'd be able to customize that by understanding all of this.
Yeah.
Okay.
So that's the kernel code that does this.
Well, first and foremost, it allows you as a kernel developer to do what you want. Mm-hmm. So when you implement a system call, either a standard system call or through a character device, and you get an interrupt, you need to ask yourself, okay, how am I going to handle this interrupt? And if there's no way to handle, you'll do uninterruptible sleep and fuck you the D. Yeah. If you can interrupt, then you say, okay, which type of interrupt do I exit? Do I restart? What do I do?
And not interrupt, hardware interrupt, but signal.
Interrupt.
Okay.
Yeah. Well, so, okay, yeah, sorry. Signal to the thread which I'm serving right now.
Gotcha. Okay.
So what it's doing is, so it has this, I've got a slide on it somewhere, maybe. No, I'll have to do from here. I think I'm all over the place. Anyway, so yeah, so when you, I was going to show you. So that's a slightly simplified version of the kernel code. So the way that and this is interesting, I think, because you can do funky stuff with the way that you return from a signal handler. So when the signal handler gets called, the kernel sets up your stack, and your user space stack. It pushes a bunch of stuff onto the user space stack and then calls the signal handler. And you can see that from, if you go the sort of a more modern signal handler installation way, and you specify SA sig info, you get these 2 extra parameters to your signal handler, right? You get the sig context and the U context. I don't know why you need 2, because you can reach the second from the third, but anyway. And that looks like this. So this structure, which contains other structures embedded in it, gets pushed onto your stack, and then your signal handler is called. And so then when it returns, it will return through the return address that actually returns to a special return from signal handler syscall. They'll then unwind everything. But if you want, you can mess about with this. So this is something that we did a while ago. One of the engineers at Undo did it, which I thought was super neat, was for reasons we have to, in some cases, extend the signal mask from a little bit before the signal handler is called until afterwards with a kind of slightly faked signal mask because of the way that some syscalls work. And so in a little signal handler stub that we install, we would put the fixed up signal mask back into that bit on the stack so that when the signal handler returned, it would get the signal mask I wanted. So I could do something wild like say that I only want this signal handler to run once. Now, actually, the way you do that is you specify SA one shot, but let's pretend that doesn't exist. Then from your signal handler, you could mask the signal in the struct that you're returning to, and then that would all be now masked when the signal handler returns. But you could do anything. You can change registers. So maybe you're responding to a segv handler, and I'm going to fix something up, do some hardware magic or something, and I want to fix something up. I can then change the registers in my signal handler that will be restored when I come back. And that's exactly what the kernel does with the restart magic. At the bottom case here, it just bodges the resume program counter. Cool, eh? Where the hell was I?
You were there.
Yeah, right. So yeah, so you can, if I just do, let's run my threads program. Okay, so if I go thread all apply, no, thread apply all, print address of Errno. Now the debugger knows that Errno is special. So the thread local, they all live at a different address. The address actually is from, what's it called? Errno location. Ignore that text here, but that gives me that current thread's Errno location. So that's how that gets mapped between the Syscall and libc. Now libc has a function called Syscall, right, which you can use to call an arbitrary Syscall as long as you know the Syscall number and what arguments to pass. Even Syscall will set Errno. Okay, enough on that. Yeah, so POSIX has this kind of notion of processes and threads. Linux doesn't really. It just has the notion of tasks, and tasks map pretty much one-to-one onto threads, and processes map onto task groups, task groups, sorry. And you have a thread group, thread group, which is a group of these tasks. Thread group leader. In the old days, threads were just created with fork, with everything kind of shared. These days, there's its own clone, and then there's clone 2. I think there's now clone 3 system calls. Pthread mutexes and condition variables and all that stuff, all built on this one kernel primitive called the Futex, which is just, I don't know whether it's beautiful or awful, or both, probably both. It's very confusing. There's a great paper called Futexes Are Tricky, where in the original proposal for Futex, they had an example of how to implement a mutex with a Futex, and it was wrong. There was a race in that original proposal. But everything's built on Futex and Futex 2, and yeah, Futex is one.
It should be pointed out that the pthread implementation of mutex, before it goes to the kernel, does a few iterations of log-free algorithms.
Yeah. So if you can get in the common case, hopefully, that your mutex is uncontended, then pthreads will not need to make a system call. You can just do that all in user space, and then only if it's decided, no, I'm not going to get this, it will block calling on Futex. And then when it comes back, it will know that it's done that, and it will wake up, or know that other threads are waiting, and it can wake up other threads using Futex. Futex is one of these horrible system calls. Ptrace is another, which I always think it's a smell of API design. First argument is an opcode. There's loads of different types of Futexes, and there's loads of different Ptrace calls. I don't know why they do that. I don't think we're going to run out of integers. But anyway, it's just something to know that if you see something stopped in Futex, it's probably in a lock, probably in a pthread lock somewhere. Yeah, this is just something I found interesting. So older versions of libc would just cache the PID. When you do a fork, it would, in the child process, it would just say, right, well, what's my PID? Actually, I think the first time you call get PID, but anyway, and it will just store it there in a global variable because the process ID is not going to change. I can just store that in a static global variable, and that was all good until some people started doing some of the stuff we've seen here and bypassing libc and just calling fork directly, and the cache wouldn't get cleared, and cache invalidation being one of the 3 hard problems and all that. And even there was a bug in one of the clone implementations that didn't anyway, it was a mess. And so in the end, they decided just don't do that anymore. So modern versions do not cache the PID. They will just, if you call get PID in just normal libc get PID, that will translate into a get PID System call, there are ways you could do it. I think you could, this was actually from a suggestion on Stack Overflow I saw, you could just, as a memory, an mmap attribute, map the wipe on fork, you could set that. You could put your cached PID in such a page and that would automatically work. Or I don't know why we can just store it in the VDSO or in Viva, right? Kernel could just tell you what it is.
No, you can't. Because the VDSO is shared to...
Not VDSO, you're right, but Viva. I think you could go in Viva. Yeah, and you're right, and that's the difference between Viva and VDSO. But it doesn't. Linus had a big rant about why it was a stupid thing to do and no one should ever need it, so I guess that's not going to happen. I guess that's how it is. Or you could store it off TLS, actually. Yeah, Linus had a big rant about how no sensible application would ever need to get PID a lot. Only like benchmarks. And I don't, yeah, it's a dangerous thing to say, but I don't agree. I mean, we have, like probably everybody in the world, we have our own logging library and we like to prefix PID and TID before the log messages. And it's really useful if that doesn't take loads of time. So actually, I think there is a legit case for doing this, but I suspect Linus has nailed his colors to the mast a bit, but we'll see. Yeah, process states is what you see in proc. Proc status, and as we were just discussing, yes, dreaded state D of uninterruptible. There are two T states. So if you stop a process with sig stop or sig T stop, or the other one, sig TTOU, like terminal things. So if the process reads from the terminal when it's in the background, or if you do Control Z, you get these job control signals, and they will stop the process and everything, and all the processes in that process group, and they'll be in a special T stopped state, unless it's being ptraced, in which case it goes in lowercase t, which is a slightly different stopped state, but not meaningfully. Yeah, so we spoke about this a bit about this, probably enough. There is all of the modern signal in syscalls have the prefix RT, sig action, or RT whatever, sig return, RT set, sig stack, all that stuff. Yeah, you should just always use those. The old ones are just sort of there for backwards compatibility purposes. Actually, one thing I meant to say, I mean, so we've been doing this for a long time now, and I have to say, the Kernel ABI has remained remarkably stable. Like, they really, really do a good job at maintaining backwards compatibility. I spoke to people at Microsoft who made their time travel debugger about some of this stuff, and it turns out on Windows you can't do this trick of intercept all the system calls and then reconstruct the states, because even though on Linux there are like many hundreds of system calls and they're all weird and it's all mad, Windows is just like a whole other league. And there are thousands of system calls. No one knows what they all do, including anybody at Microsoft. And they change, right? There's no stable ABI. So yeah, I think I've come to the conclusion that the Linux kernel has the worst ABI of all operating systems, apart from all the others.
By the way, on Apple, on the Mac OS, they will not let you statically link the libc.
Ah, right. Okay. So they can
freely play with
mess around with it. Yeah. So we'd be hosed, I think, in that situation. So they do a remarkably good job of maintaining backwards compatibility. There's only been a handful of times over the years where a new kernel has come out and like broken stuff that used to work. Like, they add stuff that we have to support all the time. They really keep everything around. The only exception is if there are security reasons, which have actually with, I think it was the row hammer attack or one of those, where some stuff stopped being exposed through proc. We kind of piped up on the kernel mailing list and said this was bad for us. And Linus himself jumped in and they had a workaround solution like within, like the day. So you really do a remarkably good job. Yeah, that's what I was looking. That's the slide I was looking for before. I think we've covered like all of this. So yeah, we talked. I think we covered all of that stuff. All right. Yeah, Auxv, NP, and Auxv. So the first bit of this probably isn't surprising. So this is the stack. When you start your program, like with exec, and you get into main, this is what the stack looks like. Right? You've got argc, and then the arguments after that, your environment variables, and then this mad thing called Auxv, and then other bits and bobs.
What is Auxv? You're welcome.
Yeah. So I think the reason why most people, like even you are not familiar with it, is I don't think it's terribly useful for most of the time. So it's basically just a bunch of key value pairs, integer types mapping onto things. So you can go get Auxv val, and this will tell you about all the things you can see. So AT clock tick.
I actually wanted to use one of them.
Okay.
The address of the.
Yes, that's the only one I've ever used. Yes.
Right.
Yeah. So there's where's it called? P header. Yeah. So this gives you an address where you can look at the header for the elf, and what you might want to do is mad stuff with that. The rest of it you can just get from proc, like cache size stuff, hardware capabilities.
No, it has the address of the system call enter in VDSO, I think.
Yes.
That was the one I needed.
This one? Is that sysinfo? Yeah. Okay, yeah. I've used the P header before. If I do my lightning talk tonight, I might mention it. But yeah, most of it. So it's just stuff that the operating system thinks your process might find useful. But most of it you can get from proc. Okay, Ptrace. So I've talked a bit about it because, as I said, one of the main purposes is trying to debug things when things are mad, and then you're often going to be relying on something built on top of Ptrace, even if you're not writing Ptrace yourself. The Ptrace API is just the worst, but the kind of concepts of how it works are very sensible, I think, largely. Right? So the API is horrible. It's inherited from some Sun stuff that was, so it's sort of, they just forklifted the old Sun OS API and then started bolting things onto it. So the actual way you call it is a mess, but the principles are pretty sensible. So when something's running under Ptrace, so in my example here, I've got GDB, I'm debugging hello world, and I'm stopped at the GDB prompt. So my hello world application is stopped. It's in this Ptrace stop state, not doing anything. And then I issue a call Ptrace cont, that will set it running. Usually, doesn't have to, but usually the debugger or whatever will now block waiting for something interesting to happen, which is always a signal. So the target process receives some kind of signal, and then that will then cause GDB to wake up from its wait and then kind of decide what the hell is going on. Even a breakpoint or a watch point, that will turn into a sig trap. If you do Control-C at the keyboard, like I did with that read example, kernel turns that into a sigint, but it gets fed through. It's really the only way the debugger is going to get control back. If the debugger decides preemptively it wants to get control back, typically we'll do so by sending sig stop to the target and waiting for that to come back. Question, Richard?
And then is hello world in this example signaling GDB, like on that control signal, so it had a signal, your example.
Yeah.
The kernel gave an interrupt to hello world, but then the debugger needs to know it. So does it need to go, oh, hey, by the way, just so you know, I got a signal. It signals GDB from the process, or does the kernel signal GDB?
Kind of the kernel. So in the case where I could Control-C, or even hit a breakpoint, for the most, usually, the target process will be completely unaware that signal happened. It'll just and I'll get into this in a minute, but the tracing process has complete control over what signals the target actually gets to see, so it can kind of filter in this way.
Is that by injecting code inside the process that it runs when the signal happens, or is it the tracing program GDB tells the kernel, hey, I'm tracing, so redirect the signals over to me?
Yeah, the kernel, just like in the signal code for the
It's
kernel.
not redirected. The original process still gets all the signals, but before it arrives at them, the GDB gets a SIG's child. Not all of this, it gets the same signal, and then it can use ptrace to find out what happened, and then it can say, when it does continue, whether it allows the signal through.
Yeah.
So you put a breakpoint, hello world gets SIG_trap, your process gets SIG_child, it sees that the hello world got a SIG_trap, it says, oh, that's my breakpoint. So when it does ptrace continue, it doesn't let the SIG_trap through, and hello world continues as if it received no signal.
Yeah. The only slight difference on that is that, so GDB or whatever will call waitpid, and it will actually see the SIG_trap or something returned from waitpid directly. It can then probe more information about that by doing a ptrace get sig info. But yeah, it exactly. So the tracing process completely controls which signals get observed. It could be feed back in, or it can just throw them back in. So that GDB, there's a signal command. I can just type signal sig user1, and it will just fire that at the target process. Yeah, if the debugger or whatever decides it wants to interrupt the target process, it will generally do that. Usually, will do that by sending it with the regular kill, tkill or tgkill. It will send it sig stop. Anyone want to guess why sig stop is the right choice?
It's not maskable.
handleable.
It's not maskable and not handleable, exactly. Yes.
Just a question, how are usual breakpoints set? Because on Windows, I remember it's just, it changes the executable by putting in like an Auxv.
OXCC. Yeah.
Oh, okay, yeah.
I didn't think we were going to get into opcodes today, but yeah, let's probably.
Yeah, is it the same in Linux?
Yeah, exactly the same. Okay. Yeah, it's really dictated by the CPU vendor. There is another way. So on x86, it has some debug registers. So you can have what are called hardware breakpoints, which don't modify the program executable, but you can only have up to 4 of those. Okay. So for the most part, it just stuffs this magic OXCC opcode, which is special on x86 because that's an int3. So it does a software interrupt of 3. Usually, software interrupt is 2 bytes long, and that won't work for breakpoints because you might have, because x86 is variable length instructions, and there are lots of single byte instructions. So I need to have, so the good people at Intel actually thought of this when they designed the original x86 instruction set. I need to be able to put an int something with 1 byte. So int anything other than 3 is a 2 byte instruction. Int 3 is a 1 byte instruction, so that I can put it in without, I can have 2 adjacent instructions and things like that. Yep.
So related to that, the signal handler, is it overwritten? Like, do you go and physically override the signal handler in the hello world?
No.
Or is this a special mechanism that allows to? So the OS knows to send to the
kernel. It's all within the kernel. And if you look at the kernel, dare I do this? If you look at signal.c in the kernel, what you see that like whether the application is being traced, it's like all over this file. Like I haven't counted, but probably more than half of signal.c is dealing with the special case, unusual case that the process is being traced. And it just does everything differently. So yeah, we talked about all of this, I think. Yeah, so this is the signal delivery algorithm, right? This is roughly what the kernel does. So if the signal is being sent to the process, sig_kill, that's it. The process is dead no matter what, unless it's in this uninterruptible sleep state. Even if you're being ptraced, there's nothing you can do to stop that. Otherwise, if it's a sig_stop, it's going to suspend the process. Again, there's no part of a signal handler. You can't get in you can't feed it back in, so it's definitely going to stop the process. And then if it's being ptraced, all the special stuff happens. If it's being blocked, we mark it pending. There's 2 pending queues, by the way. So if we look in what we see is, so these here, so this is sig pending. These are the signals that are pending for that particular task, that thread, and they're shared pending, and these are due to go to these are signals that are due to go to any thread in the current thread, group, or process. It's not sort of determined yet. Obviously, this process doesn't have any signals that are pending. That's all fine. If it's ignored, we just drop it. And if there's a handler, we run the handler. And then if not, well, depending on the signal type, we usually terminate the process, or maybe default behavior for some signals is to stop the process or be ignored. Unless, special case, if you receive a faulting signal like SIG-SEGV or SIG-bus or something like that, and you've masked that signal, or you've told it to ignore that signal, the kernel will magically, on your behalf, unblock that signal and set the signal handler to default, and then do whatever it would normally do. So if you find yourself masking SEGV and getting and then SEGVing, is why you can get sort of slightly weird behavior, surprising behavior. Kind of makes sense when you remember that when a signal handler runs, by default, the signal of that handler will be masked. You can tell it not to do that, but by default, that signal will be masked. And people like to have handlers for SEGV. They've got a pretty print, the backtrace or whatever. And it's not uncommon for that special, hardly ever called emergency panic code to itself segfault. That does happen. So it kind of makes sense to do something sane. So then you'd get a core file, probably. Yeah, so Ptrace has a whole bunch of things you can continue and get the registers and set the registers. It's like more and more, there's more of it than this, and they're adding new stuff all the time. You can basically do almost anything that you might think of with Ptrace. Okay, this is very end of getting towards the end of the talk. It's just something I just tried to crowbar in here because I thought it was relevant, and it's caught me out on a number of times. I always forget how this works. So let's say I've got a process and it's got a file descriptor open. There's a file descriptor table inside the kernel on behalf of that process. Let's say it's this last file descriptor here, and that points at a struct file. And let's say that process reads some data, 128 bytes out of that file, then they go into the process and the position in that struct file updates. But let's say there was another process, process 2, that had been forked from this process. Yeah. And process 2 has been forked, or they're in the same fork tree, and so they've inherited the same file descriptor there. Those file descriptors will both point at the same struct file. So now if process 2 does a read of 128 bytes, it gets the second 128 bytes out of the file. Now if process 3 does a read, it gets the third. So they're kind of, the offset is not part of the file descriptor, it's the file object the file descriptor points to. If I then open another file with a file descriptor, even if it's the same one, could be the same file name, then that will have its own struct file thing in the kernel and its own offset. So yeah, this causes no end of pain when you fork and then the parent and the child both try reading from standard in or something. It's kind of wild.
Stuff in place that prevents this, where you don't automatically get copies of the file description.
So you can set close on exec.
CLO exec.
Yeah. Which will yeah. So yes, that's a good point actually. I should have said that. So the file descriptor table inherits not just a fork, which you'd kind of expect, also an exec. Unless you specify O close exec. Yeah. And
what's worse than the file offset changing is that flock. Locking mechanism also use the struct.
Yeah.
Oh wow! So it won't lock. I didn't know that. That's
right.
That's wild.
That's like horrible.
Yeah. That's wild.
They changed this on the Mac, I think.
I don't know.
Yeah.
Yeah, I didn't know that.
I think the behavior is it closes everything.
Yeah,
This is bad.
Sorry.
This is bad.
Yeah.
And also, if you dupe the file descriptor, same story.
Oh yes, stuff is the same thing. Yeah, you will have another pointer at this struct file. Yeah, I mean it's bad, but it's also useful. But I mean, because that's how when you're in a shell and you start a program, it's inherited the standard in, standard out of the shell, and it kind of works. It's why it's confusing as hell. For example, when you start your program from GDB, and now GDB is using same stood out and stood in as your program you're debugging, and that can get confusing. So yeah, anyway, I'm not here to cast any aspersions on whether this is a good idea or a bad idea. I just know that it is. Yeah.
Oh, I was going to tell a story, but I don't want to derail you.
Well, now is a perfect time for a
that
story.
ship is sailed.
I'm out of slides. So.
Oh, okay, cool. Yeah, I saw a situation. I did debug a situation a couple years back where we were using this legacy build system that we won't talk about, where it was pulling. Like the idea is that the main build process was pulling files out of the cache, like executables and stuff like that. And a situation like this where it's pulling stuff out of the cache, it's forking up other processes to run other build processes, and then eventually it's going to fork up something to actually run that unit test if it's a unit test. And there'd be situations where, depending on how things got ordered at runtime, you could have a child that was forked up that still had the cached file open for reading open for writing when you then tried to exec into the test and you'd get text file busy.
Right. That old chestnut. I've seen that before.
The flip side of that, I had programs that would sort of wrap other programs. And because that program might fork and do stuff, I wanted it to be on the foreground. So instead of fork and get the child do exec, a fork and the parent do exec. But now the child needs to know when the parent and all of its other children have quit. So what I did is I left a socket that the parent didn't know about because it exec, it's just an open file descriptor, and all of the forks inherited that, but the other end of that socket I had. So the moment the last son died, I got a end of a file on my end of the socket, and I knew I could exit.
That's funny.
Yeah, I mean, so you can do neat stuff with this.
I have another story, but that's one kind of the crazy stuff.
We're going to get into the whether or not you should stuff, aren't you? Any other comments, questions? So
you mentioned stack grows down.
Map grows down. Yeah.
So two things about it. Just I didn't want to derail the thread at the time, but if anyone's ever interested in this stuff, you start writing your own user space threading libraries and stuff. Two things. One, your main thread is kernel magic. It doesn't use stack goes down. The kernel has its own way of saying.
Is that right?
Yeah.
I didn't know that.
It has its own flags to say internally this is stack goes down, and I will ensure I don't collide with mmap heaps and stuff like that. Thing two. glibc has been trying to deprecate map goes down for years because it is completely unsafe. There is nothing in there that stops you from colliding with some random mmap allocated heap.
Right.
The way your pthread library implements thread stacks is it has I think it's a meg somewhere around there.
Yeah.
It's configurable, but I believe it's a meg, and it just says here's a 1 meg map. That's your stack.
Right.
Don't overrun it.
Yeah.
And also leave a guard page at the end.
Leave a guard page at the end.
If you do overrun it, you crash.
Yeah, so that you'll die, but you do, thread stacks don't go down. Try to write your own thread stacks. glibc will find you and as you sleep.
Yeah. That's a really good point. I hadn't thought of that. That there just could well be somebody else there.
Yeah. There's no way the kernel memory manager knows that. Well, it can figure it out, but there's no way.
I mean, I guess it's something that you're allowed to touch. So that's kind of okay.
So you're not overriding memory that doesn't belong to you, but perhaps you expected some other stuff.
But it's horrible to debug, yes. Which is the purveyor of debugging tools. I'm not all against that. Well, I just want to say, so if anybody wondered, just indulge me, how the hell this happened. So I was looking at it like, oh no, hang on. Here we go. So here's my syscall before the syscall, and then when I showed this step I over the system call, and then I decided I wanted to go reverse step I back to before the system call. If anyone's blown away by that concept of just running backwards in time, then go visit others. All right. If there are no further questions or comments, then I think we can break for lunch.
Excellent.